So I'm going to do a couple of questions now. I'm going to do 2019, 2017 and 2016. 2019, last year's question, was a full question, question 9. And I just have it here. It says, use equations to show that when dissolved in water, HCl acts as a Bronsted-Lowry acid and NH3 acts as a Bronsted-Lowry base. So let's start with that bit. So this is 2019. This is question 9, I think. 9b. Now then, when you put HCl into water, H2O, it dissociates into H3O plus and, of course, Cl minus. So when that happens, look at your HCl, it has donated a proton. So HCl donates a H plus. So if it's donated a proton, it's acting as an acid. The second part of the question says, show using equations that NH3 acts as a Bronsted-Lowry base. So NH3 into water. Now we know ammonia is a weak base, so if it's acting as a base, it's going to accept a proton, so it will become NH4 plus and OH minus. So the NH3 has become NH4 plus, so therefore it has accepted, the NH3 has accepted a H plus, so, which implies it's acting as a base. Okay, so that's the first two parts of the question. Then it says, explain why HCl has a weak conjugate base. Okay, so the third part. HCl fully dissociates in solution. So if it fully dissociates, it is a strong base. It fully dissociates as it is a strong base. Sorry, a strong acid, not a strong base, as it is a strong acid. Now, after dissociation, the Cl minus, which is now a conjugate base, does not accept H plus again. So it does not accept any H pluses, therefore, it is a weak. It is a weak conjugate base. Okay, that's the third bit. And then it says, explain why NH3 has a strong conjugate acid. Okay, so the fourth part. NH3 does not fully dissociate as it is weak. So it does not fully dissociate in solution, as it is a weak base. Therefore, the NH4 plus, which forms will readily donate a H plus again to form NH3. Therefore, it's a weak, therefore the NH4 plus is a strong conjugate acid. Okay, so they're my explanations. That's the first part. Now, part B is really to do with today's videos that are up on Schoology. So, the first part of the question, part B, says, pure water self-ionizes as follows. And we're given the equation for self-ionization. It says the ionic product of water measures the extent of this self-ionization, and a table of ionic product of water values at different temperatures is given. So here we can see temperatures going from 0 to 60 and kW values corresponding there. Right, first part of the question says, write the self-ionization constant expression, the kW, for water. Okay, so I'll get rid of this now for a minute. And we'll write the kW expression for water. So the kW expression, the self-ionization expression, is H plus concentration by OH minus concentration. So that's the first part of the question. This is part B. The second part of the question says, are the data in the table consistent with the self-ionization of water being exothermic or an endothermic process, and justify your answer. So based on this, could we say that this equation here, the self-ionization of water, is it exothermic or endothermic? Okay, so what I'm going to say is, well, I'm looking at it, I can see that as temperature increases, the kW increases. So I'll make a statement first. So kW increases with increasing temperature. So what does that tell me? This means that more ionization happens with increasing temperature. So more ionization occurs as the temperature rises, or as the temperature increases. So the kW, therefore, the kW, which is this expression here, if it's increasing, the kW is increasing, then it's favouring the forward reaction, which implies, if I took this as a dissociation expression, that this means that the forward reaction must be exothermic. Must be exothermic. Since the product concentration, which is the H plus and the OH minus concentration, is increasing with increasing temperature. So I could say, taking that expression given here, taking this expression on your question, I'm going to say that the two H2Os will give me H3O plus OH minus, I shouldn't have, and my delta H is going to be positive. So the forward reaction is exothermic. Okay, third part of the question. Plot a graph of kW versus temperature. Now, I've already that done, and unfortunately, guys, I don't have graph paper, so I'm cheating, and you would use graph paper. Do not use ordinary paper. I haven't got graph paper, so I have used this. Okay, so let's see what I've drawn here. I've taken the kW values are going from, we'll say, 0 up to 9, so I've taken those up my y-axis because they're the ones that are changing. That I have no control over. The temperature can be controlled, so we're going up in 10 degrees, and that's going along the x-axis. Don't forget to label the axis. So this one is the kW by 10 to the minus 14, and this is the temperature in degrees Celsius. Right, so you plot your graph. That's the first thing to do. Now, the fourth part of the question says, use your graph to predict the value of kW at body temperature, so at 37 degrees Celsius. So what I've done here is I've marked off 37 degrees Celsius on my x-axis and found a corresponding kW value for that temperature. So predict the value. So when I do that, when I did that, reading off this value here gives me about, it's about a 2.3 by 10 to the minus 14. Now I'm saying about, I shouldn't say about because it should be on graph paper. So I'm going to say that at 37 degrees Celsius, my kW is 2.3 by 10 to the minus 14. Okay, so that's part 4 of the question. Part 3 was the graph. Right, part 5 of the question says, use this value to calculate the H3O plus ion concentration of pure water at 37 degrees Celsius. So we're going to use this value, this Kw value taken from the graph to find the hydrogen ion concentration of pure water. Now remember what we know from today's work, that the H3O plus concentration is equal to the square root of the Kw. So we've read off the Kw, which means that the H3O plus concentration must be the square root of 2.3 by 10 to the minus 14. And when I put that into the calculator, I get 1.5166 by 10 to the minus 7. Right, so now the last bit. The last bit of that question says, the pH of pure water is close to 6.77 at one of the temperatures in the table. Find by calculation this temperature. So you're not reading it from the graph, it's by calculation. You've got to find this. All right, so one of these temperatures will have a corresponding pH of 6.77, and I'm going to use this idea here, the Kw idea. Okay, so I'm starting off with the pH, remember, is minus the log of the H plus ion concentration. And I'm told now that the pH is 6.77. So 6.77 equals minus the log of the hydrogen ion concentration. Now just remember that the hydrogen ion concentration is equal to the square root of Kw. So that's from today's work. So I can write this 6.77 equals minus the log of the square root of Kw. Now, if I get minus the antilog, the antilog of minus 6.77, that gives me 1.6982 by 10 to the minus 7. So that means 1.6982 by 10 to the minus 7 is equal to the square root of Kw. And when I square both sides, this becomes 2.88 by 10 to the minus 14. Minus 14 is equal to Kw. And from the table given, the Kw closest to that is 2.9 by 10 to the minus 14, and that happens at 40 degrees Celsius. So from the table, the corresponding temperature is 40 degrees Celsius.